So what's new with SpiNNaker? Yeah, I'll talk about things that are kind of been done since the last SpiNNaker release, really, but some sort of major topics. Let's see how we get on. Here we go. So the first one is the Multicore model. So you may have heard that we did the Multicore model to run the microcortical column in real time on SpiNNaker. And the idea of this Multicore model, well, I can sort of give you an idea based on the original processing. So the normal processing on SpiNNaker is that you receive spikes which set off DMAs. DMAs then receive rows which you then process, and you process them to get weights out, and the weights go into delay buffers in the local memory of the machine. And the delay buffer is basically transmitting along the weight as it goes. And when it gets to the end, the neuron can take it on a timer tick. So the neuron's been updated on a timer tick, and it may or may not produce a spike. And we also have Poisson cores, which are doing sort of very basic version of that, where they're not actually doing any reception, but they're basically deciding whether to spike or not and send out spikes. In a multi-core model, we have a sort of split cores between synapse processing and neuron processing mainly. So the spike processing all happens on a synapse core, as before, but now it isn't actually doing DMAs directly when you're receiving spikes anymore. It's actually using a timer. So the spikes are all going into a buffer. There's now a timer which is then going off and doing this same sort of synapse processing, and it still has delay buffers, but now the end of the delay buffer is actually stored in the SD-RAM on the SpiNNaker chip. So it transmits this out to the SD-RAM, and then the neuron core can receive the data from that place as well, and do normal stuff on neuron processing. So at the start of a timer tick, the neuron now has to go and fetch the data from SD-RAM and then do the processing as normal. The trick with this is that you can also do the same thing with Poisson cores. So when you've got Poisson one-to-one sort of feeding into the neurons, you can actually put that into one of these buffers in SD-RAM as well, and that can save you some processing of spikes. So it stops a lot of processing having to go on over here. Instead, you're just doing it in the Poisson process and directly feeding it into the neuron. You can also have multiple cores, and the idea of the generic work that I've done over and above what would happen with the cortical microcircuit is that you can now have as many cores as you want into this model, and that works. So to give you an idea how this will work, this actually works. This is a normal neural network where I've got a population and a source, Poisson source being fed into a normal population of neurons, and it's one-to-one connected. If you want to actually use the split model, you have to do a few extra things. Just now it's not automatic, unfortunately, so there's a bit of extra work to do. You have to use these things called splitters that we've hidden away in the system, and this is basically deciding how the population gets split up into the various cores. In this case, you can use a splitter for the abstract population vertex neuron synapses. It's quite long-winded, but that's what we've called it so far. This allows you to choose the number of synapse vertices. In addition, because the delays are now all handled on separate synapse cores rather than the neuron cores, you can actually get potentially longer delays on the core without having to use delay extensions. This here allows you to actually specify how long you want those delays to be, and you can also purposefully exclude delay extensions. So basically, this will mean if the core thinks it needs to use delay extensions, you'll get an exception saying, you shouldn't, you said you didn't want to use delay extensions, but I need one. So then you can adjust your network appropriately. So with the cortical microcolumn, these are the settings that we actually used. 3 synapse vertices per neuron vertex, and then a max delay of 128 instead of 16. So that's why we get away with it. You also, if you want the Poisson source to feed in, you have to also change how the Poisson source gets split by basically putting in this extra thing. And this just tells our software, I do actually want the Poisson to work like this. If it's a one-to-one connected Poisson and it's got this splitter, it will then process things appropriately in the software. And then for your projection, you don't have to do anything special after that. It just works with whatever you provide it. Okay, something else that we've been looking at and is now in our master code is, that is in the master code, by the way, now. So if you want to use it, it's in that code, not in the release version yet. That'll be coming soon. So we've also been working on neuromodulation. We've actually had this code around a long time from a user, from a PhD student. And basically this allows, instead of just feeding a neuron with excitatory and inhibitory input, you can also feed with reward and punishment input. When you're using STDP, this can be taken account of. So in normal STDP, your spikes lead to traces like this. So you've got pre-traces and post-traces. which then allow you to update the weight appropriately depending on how you've set things, how these spikes are done and how you set things up. But for example, here, when you've got a post spike after a pre-spike, it's going to cause an increase in weight. When you've got pre after a post, it causes a decrease. So fairly simple. With neuromodulation, you remove that direct correlation and we change it so there's actually an eligibility trace now. So instead, you get a sort of decay, which is governed by this tau c parameter, which is not super descriptive. That's what it's called in the papers. So that's what we've called it in our code. And this basically decides on how the neuromodulation goes ahead. So then you've also got dopamine spikes being fed into your system. So, and that has a decay as well. So when a dopamine spike happens, you get a dopamine trace that's decaying with a different tau function, tau d. So you can choose these two factors to get different neuromodulation behavior. And this basically then decides on how the weight is going to be affected more directly. So it comes through all the way through the STDP rules, creates eligibility, then dopamine feeds in, and only at the dopamine spike do you actually get a change in the weight. And as the dopamine is in effect, and if the eligibility changes, you're getting changes in the weight all the way through that process. Okay, how do you use this in our system? So this is a normal STDP synapse where you've got projection and you've got an STDP mechanism with timing dependence and weight dependence, initial weight of 0 in this case. We can then produce some reward and punishment populations, which are going to feed in the neuromodulation. So when these spike, that's going to feed a neuromodulation into the post neuron, post population, and do something with that. And this is how we then define the actual neuromodulation, in this case, a reward. So we feed the reward pop into the population. We can choose how it connects, as you usually do on SpiNNaker. You can choose any different sort of connector type. You then say the synapse type is actually a neuromodulation type. This has a weight of the dopamine. So this is the weight of the dopamine that's been fed in at each time. So that's how high that spike goes. These are the tau C and tau D I mentioned before. There's also a W max here because that's determining how the output weight is going to be, how big you want the output weight to go, so it doesn't just explode if you accidentally set these parameters wrong and get massive weights. You don't really want that. I think there's a W min parameter appropriately as well. And you can do the same for punishment. So the trick here is that when you're doing your projection, you specify your receptor type, and now you specify a receptor type of reward and punishment. This will work as long as you have an STDP rule associated with the post population already. So you have to specify it in this order. You can't do the neuromodulation first and then the STDP mechanism, so it needs to know what it's acting on. So that's the order that we allow currently. We've done some other work in general in our low-level code. So in our low-level code, we have these sort of weird executor workflow managing sort of processes. And when you call from our main SpiNNaker base sort of code to do the mapping on SpiNNaker, for example, calls one of these executors, which goes off to these algorithms and uses the injection context. This is a little bit complicated in terms of how it works, and it's led to some confusion in our code. So we've been stripping out a lot of that sort of complexity and just calling the algorithms really directly. So if you look inside our common code now, you can see big lists of algorithms, which will show you where things are going, and it's much easier to follow. In progress, we're actually working on a global object store, so similar to that injection, but it's a bit more, again, a bit more explicit. It tells you what's in it rather than just having a cloud of things which you might be able to select from. So this makes it possible then to feed the algorithms with these things and makes the code a bit neater again. We're also looking at simplification of our data. Currently, we do application level, we split it into the machine level. We have all these machine edges, which are complex and horrible, and it makes things very long. When I've been running the multi-area model, this takes days to generate, and it's a bit nasty. Placement and routing then happens at the machine level, so it doesn't take account of information at the application level. We're currently simplifying that, so there's sort of a single object which contains all the information that's needed, machine level a bit, but it doesn't have those machine connections because they're handled. You can sort of look at the main application connection and establish what the machine connections are going to be anyway. And then placement and routing can happen at the application level, which saves a lot of bother. And finally, one other thing that we've been working on, which is still in progress, is looking at convolutional networks. So basically, we're allowing, Pine already allows you to specify 2D structures in the software, but what we thought we could take advantage of this is saying we actually have 2D networks in the software which are actually going to do convolutions. We can then split these up into actual squares rather than splitting things row by row, which is what we traditionally do in SpiNNaker. And it means that the bits of that you need to feed into the next population. So for instance, this red dot here only needs to be fed from this square up here, because that's the only bits that affect it in a convolution. So you can reduce the amount of traffic that you're receiving again. And in addition to that, we're actually doing the convolution itself on the core. So we're, instead of going off to SDRAM and fetching connections, we're actually doing them straight on the core. And that work is in progress, but it's coming along nicely as well.